All right, sorry to come back here. I'm having a heck of a time coughing. So, exactly to switch dissimilar metals, we want to use 309 particularly. And this doesn't have to be stainless. Say we're just doing a high strength, low alloy steel, right? It's maybe not even stainless, but it's designed for like pins or bushings on equipment, heavy chain, sawmills, things like that. You're going to use a lot of bushings, and that's when you would also, from mild carbon steel to a high strength low alloy, a lot of times we'd use an E309 as well. Okay? Alright, SMAW equipment, for the most part, pretty simple, which is why it's broadly used, very effective, and it can be used in almost any application in any environment or atmosphere as well. Okay? Number one, you have a power source, electrode holder, ground. It can either be direct current or it can be alternating current. It can change polarities. But at this point, we're concerned with pumping out constant current, right? We're concerned with amperage. Direct current machine, but we're running a constant current. Versus GMAW, we're going to be looking at constant voltage. So we're going to set that electrode at 120 amps. We're going to try to maintain 120 amps, and the machine is always going to try to keep the amperage consistent, versus on wire it's the opposite. It's going to try to maintain the voltage consistent. Here's a constant current power source. So what it shows you here is here's the voltage side, and here's the current or the amperage. So it's showing you the difference between a long arc and a short arc. So a short arc, if you keep your short arc in nice and snug, okay, you have less resistance, so your voltage is fine. So your voltage is normal. The second you pull it apart, you get a little bit further long arc, all of a sudden your voltage has to go up by 10 volts to accommodate that resistance, right? Because now you have an air gap. So the air gap and the amperage is trying to stay the same. Let's just say we're at 100 here. It's trying to, or here, let's come over here, and just say we're here. We pull off of that, we're gaining resistance. It has to push in an extra 10 amps in order to keep that same distance. And we do also have a tendency to lose some amperage as well. Okay? So it's directly the exact same, but inverse on GMA. Again, they're trying to keep voltage, so the further you get away, or the longer stick out, you're losing amperage as well. Okay? So I want you to think of that. That air gap makes a big difference. Close, you've got low voltage. Get far away, it takes a lot of voltage to jump that bridge, so to say. It's going to take a lot of energy to get across that gap. Okay, so the voltage compensates for it at that point. Basically, that's what this tells you as well. You can read through this on your own. But the other part is if both of those are going up, anytime you're increasing your amperage or voltage, or your time, your speed alone, you're creating heat input into the work, right? So say I turn my amperage up and my voltage or my amperage is here. I'm maintaining a certain amount of heat, say 100 joules, okay? Or BTUs are going into this. The second I pull away, now all of a sudden I'm bridging that gap. I'm also spreading my funnel, my arc funnel, and I'm also making sure that now I'm putting in 120 BTUs instead of 100. So my heat affected zone becomes larger, my grain structure changes, all of this stuff where the variables really start to play in, okay? The slower I go as well, naturally, I am going to put more heat input in. So that's why travel speed is so important when we talk about inches per minute. Electrode, how many you should do? 6 inches should take up this much. If you're doing a really wide weave, you're going to use a whole electrode on 3 inches. You're putting a lot of heat input into that weld at this point, right? Especially in one area, versus over a long period of time or a long span of area, your heat input is going to go down quite a bit, all right? So arc current directly related to the heat input by far. Anything. Anytime we increase the current and voltage, we increase the heat input as well as everything else. Advantages: simple equipment, it's inexpensive, very portable, and especially with today's technology, they make a ton of electrodes, and you can weld almost any alloys. They make aluminum rods, they make brass rods, they have all sorts of crazy things that you can do with it now, okay? Some of the limitations is it is usually slow, it does have slag removal, but again, depending on the application, you may want that slag, right? It's insulating, it's blanketing, deep penetration, so forth. Electrode storage considerations, especially if it's low hydrogen electrode. And again, 5P6010, you don't want any, or you don't need it to be in a rod oven. Number one, it's made of salt and wood pulp. You dry those two things out, it's just going to crumble, okay? Most of you look at this list of what it's there: rutile iron powder, sodium potassium, cellulose sodium, things like that. What's there? Does it need to be in a rod oven or no? Low hydrogen electrodes, particularly anything that has iron powder in it, you usually want it to be there. It preheats it as well, but there's small fine granular particles of metal within that weld, which is also why the deposition rate is high. So deposition means exactly that. We're depositing more material on the weld. So 7018 has a high deposition rate, a lot of weld, because it's partially could be up to 50% of iron powder, right? 6010 doesn't deposit a lot of weld. It's usually a deep penetrating weld. If you notice when you weld it, it's usually a pretty flat weld, rather concave, okay? Arc blow, we talked a little bit about the solutions in the text here. Doesn't really show a little bit, well, it kind of does here. So arc blow is a phenomenon that happens in the book, that happens when you're SMAW welding. Let me find it here and I'll read it for you real quick. Porosity can also result from the presence of phenomenon referred to as arc blow. While this can occur with any arc welding process, it will be discussed here since it's a common problem which plagues the manual welder. Manual welder means we're using a manual process to weld this, right, and not an automatic or something else is running it, okay? To understand arc blow, one must first understand that there's a magnetic field developed whenever an electric current is passed through a conductor. In this case, the conductor is the electrode, all right? So we're on page 3-8, bottom left, if you're following along. This magnetic field is developed in a direction perpendicular to the direction of electrical current, so it can be visualized as a series of concentric circles surrounding the conductor, shown in figure -37, which is this exact picture, okay? So what it's telling you is that perpendicular to this, when our electricity, positive to negative, is going in this direction. So I want you to think of this as an eddy current, okay? Of an eddy current within a swirl. Think of a river. The river is flowing from north to south, okay? However, as we're flowing north to south, over here what's happening, what creates this eddy current is it goes around a rock. And there's a hole or displacement. So what happens is it turns around this rock and then it starts a wave in a different direction, which actually in turn changes some of your water flow. So we can start to see this difference here as we're circling around, even though our river, our main flow is going in this direction, okay? And basically what's happened is we've got eddy currents going around our weld, or our conductor. This magnetic field is strongest when contained entirely within the magnetic permeable material and resists having to travel through the air outside this magnetically permeable material. Consequently, when welding a magnetic material such as steel, the field can become distorted when the arc approaches the edge of a plate, the end of a weld, or some abrupt change in contour of the part being welded. This is shown in figure 3-8, which we're going to look at here in a second. To reduce the effects of arc blow, there's a few things you can do. Number one, as the inspector, you want to look at some of this. Change from DC to AC possibly, so you're switching fields consistently back and forth from positive to negative. Hold short of an arc as possible, okay, so that you're not creating a large gap to jump across. And this is also why 6010 is very susceptible to magnetic arc blow, because what do? You whip and pause that to be able to control the amount of heat input, and it creates a large field for it to for this phenomenon to happen, okay? Reduce welding current, you can turn it down a little bit, you can angle the electrode in a different direction, which most of you have done by the time you've done weld 2. Use heavy tack welds at either end of the plate so that it will help create this gap here, Okay, it'll help create this magnetic field. And then use a backstep technique sometimes. Weld away from the work connection to reduce backflow. Okay, so number one, think about this. If you're welding towards it, say your ground clamp is here and you're welding in this direction, what's happening is your magnetic field is this big, and all of a sudden your magnetic field is condensing, right? So all of a sudden the magnetism is getting much more amplified at this point. However, if you weld your workpiece is here and you weld away from it, it is that electricity, that magnetic field is contained within that entire piece, which is also important of why you need to tack weld this section here to allow that magnetic field to be out here. Sometimes in multiple places and locations will also help with that magnetic field being consistent too. So my ground is here, I'm going to weld away from it so my magnetic field is opened up and it's more consistent. Most of us have done 70-18. By the time you drag to a T-joint, your 20-degree drag angle, and all of a sudden at the end I've told you straighten this up and kind of push it this way. And what happens is you're changing a little bit of the direction so that magnetic field also can kind of come back in this way. Okay, it can open back up instead of being condensed in that manner. All right. All right, SMAW discontinuities. Number one, porosity. Porosity is in anything. Trapped hydrogen, moisture, air. Trapped hydrogen is what porosity is. And when the other thing is you're in weld inspection technology now, so we're very critical about this stuff. You need to know the definitions. And at the end of every one of these modules, there's definitions. Particularly on porosity. What is it? It's in trapped hydrogen. I'm no longer going to accept bubbles. Okay? This is an entirely different course. This is a very advanced course. We are making sure that we're using the proper terminology and close to the identical situation. Okay? Weld 1, Weld 2, we get okay with some gas bubbles, you know, holes in the weld. I kind of understand. I accept a little bit of that in the beginning, but we're at the advanced stages now, no longer acceptable. Okay? Slag inclusions, also don't want to hear anything buried in a base metal. That's, air inclusions is what? It's a porosity. That's what air inclusions are. This is particular to slag. Now there can be multiple things within slag, be, you know, wood, grease, grime, so forth. However, this one is slag as well. Okay? Normal inclusions would be a foreign matter, spatter, incomplete joint penetration, incomplete fusion. Okay? Particularly the one that almost all these apply to every weld, with the exception of slag. It only applies to something that has a flux. Okay? All right. Sorry, making sure that we're still rolling along. GMAW, gas metal arc welding. All right? It's great for another thing. If you notice, we're inside of a shop, facility where we don't have a ton of atmospheric air and conditions. Okay? Here's a schematic of it. Naturally, a couple things. You got a shielding gas, you've got to be the wire being fed, and then you also have electricity. So you have three things within that nozzle and gun that you're talking about, right? So some people get frustrated about there being a very large gun sometimes and why it's so big. But particularly if you're going to run flux core arc welding or spray transfer, you're running a lot of amperage in there. You're going to need a large wire here in order to run that amount of current for a long period of time. If you're running short circuit, then it's easier to get it within a small electrode holder. But you know, larger circuits, larger amperage, higher heat, we need larger guns, and that's why they're designed that way, to be able to handle that amount of pressure, amperage, and so forth. All right, moving on. In this case, you can, in this case it's showing you're dragging it along. Most of us have dragged it. You can push it in certain situations as well. Naturally going vertically, you're pushing it up most of the time. GMAW can usually be used in an uphill or a downhill progression. It depends on technique at this point. You have a wire guide that's helping you. Contact tube is actually where it makes it. We're going to talk about that here in a minute. You have an outside shielding gas, and this is your only gas to shield. Okay? There's a little bit on this wire. Think about that wire alone. It's a 70S steel wire just like 7018, but when you look at it, it's actually copper, right? So it's coated in silicon, a bunch of other little chemicals in there to keep it from rusting on the roll while it's sitting in the shelves and so forth, okay? However, that little brown film you get on top of the weld a lot of times is that silicon, everything sitting on the top. And that's why we have you grind that down, get that top 5 to 6 thousandths off of it as well, okay? All right, electrode. We're gonna talk about electrode identification system on this. First E naturally is for electrode as well. However, R means it's a rod, okay? This one can also be used, it tells you for GTAW, it has an ER as well, okay? The next two on GMAW are strength, okay? So same thing, ER70S-6 is what we run in the shop. Same thing, 70 is a minimum tensile strength of 70,000, okay? S means it's solid wire. When we get the flux core, we're going to talk about 70T. T is a tubular wire. So when you say it's a round wire, now we're starting to get critical. Again, I accepted a little bit about in the beginning, but now we need to know that T or that S tells us is it flux core or is it not, okay? Then the last one is a definite chemical composition. There's several of them in here, 1 through 6. I believe there's actually more if I remember right. Most of what you're going to see is the 70S-6, most compatible. 70S-2 and 6 are usually the ones that can be used for TIG, whether they are done with TIG and also can be used with oxy-fuel welding, okay? Those two positions, so most people in their GMAW filler metals run the same thing. A 70S-6 is a very common wire, and I have used actual GMAW wire to oxy-fuel weld simple things together as well. Okay, I've just spooled a bunch of it out, unwound it, cut it off, and used that instead of actually having full-size filler metal wire. All right. So GMAW nomenclature, particularly. We are on page 311 still, but technically when this picture here is on page 3-14, there's a few things I want to talk about here. Okay, number one, you have your outside nozzle. Up here you have your diffuser, which the air comes out. Okay, so the diffusers we're always talking about, when we start getting porosity, start here. Look at your nozzle, is it blocked? If it's blocked, if it's not blocked, then we go to the diffuser. If it's not blocked, then we look in the liner. Work your way back to the machine and your power source or your gas source, okay? Same thing, gaseous shield comes down through here. Here's your contact tube, which is the center, okay? So here your gaseous shield can come out and it covers a blanket in this direction, which is also really important to think about your angle and electrode manipulation as well. You don't want to go so fast that basically you're not getting any coverage, right? And if you turn your gas up so high, guess what happens? The air comes out and it can hit it and it create a turbulent flow as well. So too much gas pressure or too high of gas pressure and volume can also create a lot of porosity, a really weird weld puddle, and cause its own issues, spatter and everything else at the same time, okay? Now, we talked about the gas, its effects, the nozzle. So now we're going to go to the center section, which is our electricity ties into this contact tube, okay? So this contact tube threads into the electrical conductor, and the wire is fed in the center. So where does it actually make electricity? Where do the two combine? On a 7018 or 6010 electrode, we come out of the positive end of the stinger, we run the charge down the end of the electrode, and then it actually creates the spark at the end of the electrode to the base metal. Well, where these two join right here is exactly this, the contact tube. And most of you told me, if that contact tube is no longer round, right? It's no longer a round shape, it's actually ovaled, then we're starting to lose voltage in here in the center to where it's not making a good connection between those two. We might be losing 1 or 2 volts in that contact tube, which creates for an erratic arc, erratic weld, and many of the problems that we've seen while we've been welding at this point. I've seen people try to maintain that contact tube for, almost throw my friend almost threw his welding machine away because he hadn't changed that contact tube. And he said, oh, this thing's welding like a pile of junk anymore. And I went in there, and my goodness, it was like for like a 070 wire. And he was running 030 wire for his household machine. Well, he had to turn it all the way up just to make a simple weld because it wasn't making that connection. Again, the electricity makes the connection here. This is why it's considered a consumable. Sometimes multiple times in a day we'll have to go through those. Some of us are better welders than others, and some of us in a few minutes we may have to go through that. But this is a good indication of where we start to have some problems as well, okay? Seeing an erratic arc, lack of fusion, lack of penetration can create spatter, inconsistencies, and so forth. So one of the big things I want you to think about here is a lot of times when you read and wire, okay, the manufacturer's directions, what the stick out is and everything else, what does this weld the best with? What type of gas flow does it need? What type of nozzle? So forth. Usually you start to kind of know and you can kind of weld and try. But if you're reading through this prints, a lot of people look at the stick out very different, okay? The stick out is technically from your nozzle to the end of your electrode, okay? So if my contact tube is in the back side of my nozzle, say there's a 1/4 inch or a half of an inch, 1/4 to 3/8 of an inch between this and here, and then I've got a 1/2 inch here. My full stick out is almost like an inch at that point. And at that point, that's considered my electrode extension, okay? And it might say your electrode extension needs to be within a 3/8 of an inch. So you have to remember that these two things combined, your stick out and your electrode extension, both of these are the electrode extension. The stick out is only from your nozzle here. Now certain wires, and most of you have done like a groove plate with me to where it's hard, that nozzle's pretty wide and big, and it's hard for you to get down in there, right? Into that deep groove like a 3/8 groove plate or that 1-inch groove plate on a flux cord. And what have I done? I've got you a contact tube that's stuck out here a little bit more, so you're not losing your voltage. You're getting that stick out here of that 1/2 inch, so you're getting a good, consistent, stable arc at that point. However, sometimes that can create some issues with gas, especially if you're running a high gas flow, okay? And you don't want to get out there super far either, okay? Make sense? I think so. Most everybody's done pretty good with that by the time we explain it here. All right? Naturally, GMAW does require a little bit more equipment. Number one, you got to have a power source that's capable of creating constant voltage, which not all machines are. Okay? You got to have some sort of a wire feeding mechanism, somewhere to store your wire, even if it's a spool gun on the hand, right, for aluminum. That's still a wire feeding mechanism, whether it's pushing it or pulling it. Got to have a set of rollers, a liner, and we refer to that flexible tubing within it as a liner, and that's what our gas is transferred through as well. That liner can wear out and create some issues also, okay? Other than that, it's the same as everything else. It needs a power source, it needs a ground and a positive in order to make that electrical connection. It is an arc welding process, okay? But it also has to have shielding gas. In this case, GMAW is definitely gas metal arc welding, gas shielded, okay? All right, constant potential power source, same thing as we talked about earlier. Move on, go through it. Self-regulating, yeah, I don't know about that. One of the biggest things is a lot of people will say that wire feed speed is directly influenced. It is your arc, your amperage. It's not exactly the same thing. So as we know, we're trying to feed a consistent voltage here, right? So as your voltage is trying to stay consistent, what happens here is, say your inches per minute, your current amperage can go up or down.